Okay, hello and welcome to this online lecture for my HUP 112 Logic and Philosophy class at LaGuardia Community College. So this video is primarily intended for students in that class. And today we're going to be going over some exercises from the textbook that we're using, which is A Concise Introduction to Logic by Patrick Hurley. I think this is the 13th edition. I don't know. So the exercises stay mostly the same. Sometimes they change a thing here or two, here or there, but not too drastic. So the instructions tell us to use truth tables to determine whether the following symbolized statements are tautologous, self-contradictory, or contingent. So we've been studying truth tables. And we, of course, remember what tautologous, self-contradictory, or contingent means. So when a statement is, when a when a statement is contingent, I don't have my pen here. I'm just not noticing. But when a statement is contingent, that means that there are some cases in which it is true, and some cases which it is false. Which in our way of doing things means that on the truth table there will be some T's and some F's, keeping in mind that some means at least one. So there's at least one line where it's true and at least one line where it's false. A statement is self-contradictory when every line on the truth table is false. There's no way for it to be true. And a statement is tautologous when every line on the truth table is true. There's no way for it to be false. So we went over these and we've been studying them. Now we're going to use our truth tables to classify these. So I'll be doing the starred exercises. These exercises that have stars have answers in the back of the book, but I think it's useful to see someone go through them rather than just have the answer being told to you. The rest of them are left for your homework assignments, and then we go over them in class. If you have any questions about this, you can leave a comment on this YouTube video or send me an email at my LaGuardia email address if you're in the class, which this is primarily intended for. Okay, so let's go ahead and get started. So this number one says N horseshoe parentheses N horseshoe N. So that's a weird thing to say, like if it's raining, then if it's raining, then it's raining. So that's a weird sentence, but perfectly well-formed according to the rules of propositional logic. So we remember the rule for constructing truth tables. The number of lines that you have equals 2 to the n, where n is the number of propositions, and 2 is the number of truth values. So since we have 2 truth values, this number is 2. If there were 3 truth values, it would be 3. So since there's just one proposition here, 2 to the 1 is, of course, just 2. So we just need 2 lines for this truth table. It's not too onerous. We write n horseshoe parentheses n horseshoe n. We know there's going to be 2 lines for our truth table. That's the case where n is true. That's one scenario. Remember, these lines here mean conditions under which n is either true or false. So scenario 1 is where n is true, and scenario 2 is where n is false. And we write the same thing under each occurrence of the same proposition. And then we use the horseshoe rule. The horseshoe rule tells us that it's going to be false when the antecedent is true and the consequent is false. So true and true with the horseshoe makes it true, and false will also make it true. And then true and true makes this true, and false and true makes that true. And so then we circle the main operator here. This is a tautology because every line on the truth table is true. Now, if you don't remember the rule for horseshoe, it's in the textbook, but also I have the lecture on propositional logic, and then also the propositional logic in ordinary English, which you can go back and review. All right, so the answer to number 1 is that it's a tautology. That's very good. Let's go ahead and look at number 4. Still fighting these allergies, so you're going to have to excuse me for that. So this one's a bit more complicated. We have a bracket and a parentheses, and it says E horseshoe F in parentheses, horseshoe F, and then a bracket, horseshoe E. So remember that every horseshoe statement simply says P horseshoe Q. So in this case, the P part is equal to parentheses E horseshoe F, and the Q part is E, And then if you substitute these in place of P and Q, this says just P horseshoe Q. So that means that ultimately we're going to be using our um, truth functional definition of implication to solve this. But first, we need to construct the regular truth table before we do that. And of course, we have two propositions. So that's 2 to the 2, which is 4. So we're going to need 4 lines for this. So we write out the 4 conditions. And the 4 conditions are, we know we write 2 truths and 2 falses under the first proposition, and then alternating truths and falses under the second proposition. And then we're going to keep those everywhere we go over here. So under F, we're going to write true, false, true, false. And under E, we're going to write our 2 truths and 2 falses. Then we go inside the parentheses and compute E horseshoe F. So that's true, false when the antecedent is true and the consequence false. And then true, true. And then we're going to take this and look at this. And true with the horseshoe makes it true. False and false with the horseshoe makes it true. True and true is true. True and false is false. So now we want to take this and apply the horseshoe rule to it. So true and true with the horseshoe is true. True and true is true. True and false is false. And false is true. And then, of course, we circle the truth values for the main operator. And what we can see is that sometimes this is true and sometimes this is false. So sentence number 4 is a contingent statement. Contingent is just a fancy word that means it depends. And in this case, it depends on what the propositions are, because if E is false and F is true, then this sentence will be false. But in these other cases, the sentence will be true. So it depends on whether the sentences say something true or something false. Tautologist statements or self-contradictory statements, they don't depend on what the statements themselves say. They're true or false completely as a matter of the definition of the logical operators. Okay, so that's well and good. Now we'll go ahead and do number 7 here. So we have ZX and Z and X. So again, this is just our 4-line truth table. So let's write it out. We'll do it the other way, just so we remember that there are 2 ways to do this, separating the propositions out. And I'll try to make this as explicit as possible. So we have Z horseshoe X, Z horseshoe X, and then we have X wedge Z. So X wedge Z. And then finally, we have Z horseshoe X dot X wedge Z. So then we can just take these 2 columns and write a dot between them. So Z horseshoe X dot X wedge Z. And then that'll give us this. And then finally, what we want to do is write all of this horseshoe to X, which we'll write here. So that's brackets, parentheses, Z horseshoe X dot parentheses X wedge Z parentheses bracket horseshoe X. Oops, there we go. Okay. And since we only have 2 propositions here, we know there's going to be 4 cases, same as before. So notice that what I did here, this is just an alternate way of constructing the truth table. So I took each part of this statement that we ultimately want to do, and I broke it down so that I don't have everything written underneath these things. That is perfectly fine if you want to do it that way that we just did previously. If you want to keep things a little bit neater, this is another way to do it. Where you don't go cross-eyed, hopefully. Okay, so Z horseshoe X using Z and X. So that's true and true with the horseshoe is true. True and false with the horseshoe is false. When Z is false and X is true, Z horseshoe X is true. And when Z is false and X is false, Z horseshoe X is false. Okay, now we want X wedge Z. So when X is true and Z is true, X wedge Z is true. When X is false and Z is true, X wedge Z is true. When X is true and Z is false, X wedge Z is true. And when X is false and Z is false, X wedge Z is false. That's just according to the rule for the horseshoe and the wedge. Now we will put a dot between these two columns. So the dot is only true when both of them are true. So here is true, false and true with the dot is false. True and true is true, and false is, of course, false. Now we can take this and horseshoe it to X. So here's X. So when parentheses Z horseshoe X, parentheses dot, parentheses X wedge Z, parentheses is true, and X is true, this whole statement is true. When this is false and that is false, the whole statement is true. When this is true and that is true, the whole statement is true. And when this is false and that is false, the whole statement is false. So this, of course, is a tautology. Every line on the truth table turns out to be true. Okay, so that's, of course, what we would write on a test or exam. We would say this is a tautology. Every line on the truth table is true under the main operator. So we not only have to say the answer, but explain it so that we can show that we understand what we're writing. That's how you get full credit on these kinds of assignments. Okay, very cool. So 10 and 13 we'll do. These ones are a bit more complicated, but applying the same rules. Oops, where's my pen? There it is. Okay, so we have brackets, G, horseshoe, parentheses, N, horseshoe, tilde, G, parentheses, bracket, dot, bracket, parentheses, N, triple bar, G, parentheses, dot, and parentheses, and wedge, G, parentheses, bracket. So what do we have here? G and N, that's it. So this is a pretty complicated sentence, but it ultimately turns out to just be more of the same. So we'll write it out up here. We have our brackets. We have G, horseshoeing, parentheses, N, horseshoe, tilde G, parentheses, bracket, dot, bracket, parentheses. Oops, sorry, I want to give myself more room than that. So parentheses over here. Where am I? Parentheses, N, triple bar, G, parentheses, dot, parentheses, and wedge, G, parentheses, bracket. So we know we have two propositions. So we're going to have 4 lines of the truth table, drawing those out. So here I'm doing it the other way, where I'm going to have a bunch of stuff written under each column. But really, it just depends on what makes you happy. So G, we're going to write 2 trues and 2 falses. And under N, we're going to alternate trues and falses. And then we're going to keep those the same for every one here. So since this says tilde G, I'll just apply a tilde to this one. So I'll write false, false, true, true. So then I can compute the truth values for the horseshoe here. So true and false with the horseshoe is false, true, true, true. Now I want to look here and here with the horseshoe. So true and false with a horseshoe is false, true and true is true, false and true is true, and false and true is true. So ultimately what I'm going to do is I'm going to look here under this horseshoe operator and this dot operator to get the main one. But now we will do N triple bar G and N wedge G. So we have G and N here. I'm not really going to rewrite them. You could, if you really wanted to, rewrite them. So the triple bar is one that I don't really put on the exam. I don't really care about it. As I explained in class, it really is a conjunction of horseshoes going in both directions, and you don't really need another operator for that, although it's fine to have it. But since it's on the homework, we remember that it's true only when the truth values match. So when it's true and true, we get true. When it's true and false, we get false. And when it's false and true, we get false. And when it's false and false, we get true. So that's the N and G with the triple bar. And then the N and G with a wedge is going to be true when they're both true, true when one or the other is true, and false when they're both false. Sort of the standard for those. And then applying a dot between these two, we need both of them to be true. And of course, that's only the first case up there. So now we have our our two cases that we want to look at for our dot, our main operator. So we have false and true, that makes false. We have true and false, that makes false. We have true and false, that makes false. And we have true and false, that makes false. So this sentence is self-contradictory because every line on the truth table is false. Okay, so that's how you do that. So we got one more to do in this section here. So let's go ahead and do that after I erase this. Now this one I think is going to require more lines of the truth table. So I'll have to write a bit more parsimoniously, more succinctly, smaller even. So this one, number 13, we have U, T, and S. So that's going to be 8 lines of the truth table. And we see that the main operator here is this triple bar. So let's go ahead and write this out. We know that we're going to need 8 lines. So let me just make sure I can fit 8 lines. 2, 3, 4, 5, 6, 7, 8. Okay. So we know there's going to be 8 lines, and we have this big statement here. That's a bracket, U dot, parentheses, T wedge S. That's in brackets connected by a triple bar to this thing over here, which is bracket parentheses tilde T wedge tilde U, parentheses tilde T wedge tilde U in parentheses, and then that's dotted to, in parentheses, tilde S wedge tilde U. Can I make that bigger? Does that work? Okay, I think that works. And then, of course, we need a bracket to make that a woof, well-formed formula. Okay, so now we're going to have our 8 cases here. Alrighty, so I need to draw these lines, otherwise everything goes sideways. 7 and then 8. And now under U, the rule says take 4, your total number of lines, divide it in half, and then you write even numbers of trues and falses. In this case, it's 4. 1, 2, 3, 4, and then 4 falses. 1, 2, 3, 4. Okay, and then under T, we take the number 4, divide it in half. Now we have 2 trues and 2 falses. True. And you just repeat that till you get to the end, always starting with true and ending with F. And then under S, we divide 2 in half. That's 1. So we alternate trues and falses. By the end, you're always alternating. And this pattern repeats, as you know. So if there were 16 lines, you would write 8 trues and 8 falses, and so forth and so on. Okay, so over here we have the tildes of these. So I'll just go ahead and reverse those. So tilde T over here is going to be false, false, true, true, false, false, true, true, applying a tilde to that. So we'll write that here, false, false, true, true, false, false, true, true. And then the U is going to be 4 falses and 4 trues, applying a tilde to U. 1, 2, 3, 4. 1, 2, 3, 4. And then S is going to alternate false, true, false, true, false, true, false, true, false, true, false, true. And then the U was the same, 4 falses. 1, 2, 3, 4, and then 4 trues. 1, 2, 3, 4. All right, so now we have everything filled in. Ultimately, what we want is to look at this dot, the column under that dot, and the column under this dot, and apply the triple bar rule. But to get to there, we have to do the stuff inside the parentheses. So first we can do T wedge S. So true and true with the wedge is true. And true and false is true. And false and true is true. And false is false. True and true is true. True and false is true. False and true is true. False and false is, of course, false with the wedge. Don't confuse the wedge with the horseshoe. So now what we want to do is look under U and under T wedge S, which is this column here, and apply the dot. So when it's true and true, we get true. True and true, we get true. True and true, we get true. True and false, we get false. False and true, we get false. False and true is also false. False and true, false. False and false is false. Okay, so this is ultimately the one that we're going to want to pay attention to. So that's here, just to star it so that I don't lose track of what I'm doing. Now we'll compute this dot here by first doing the parentheses. So false and false with the wedge is false. False and false is false. True and false is true. And these ones are going to be true all the way down. Okay, and this is the one we're going to be looking at here. So now this wedge operator in these parentheses, that's false, true, false, true, 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 true. Now we have this. So the middle column on each of these, and we're going to get the dot. So false and false with a dot is false. You need both of them true. False and true is false with a dot. You need both true. True and false is false. True and true is true. True and true is true. True and true is true. True and true. And true and true. So now we have this one, which is going up in the middle. And now we apply the triple bar operator, which says that we have to have matchy-matchy, false and false or true and true. So let's make sure this is a star. So with true and false, we get a false. And line 2, true and false, we get a false. And here, true and false, we get a false. And this is false and true, we get a false. False and true is another false. False and true is another false. False and false is a true. And false and true is a false. So there is one line where this statement is true, and that makes this a contingent statement. You don't need to have a bunch of trues and falses for it to be contingent. You just need to have one where it comes out that way. So sometimes people get a little squeamish and go, wait a minute, there's only one. So does that mean it's self-contradictory? Nope, there's one condition under which this thing is true. And it's the condition where U is false and T is false and S is true. Okay, very good. So let's go ahead and get rid of all of this here and then go on to the next section. So truth tables are a bit annoying. There's no doubt about that. But once you get the hang of them, they lend themselves to silly mistakes, but they are not the most difficult thing that we will do. They are tedious and time consuming, so they are not fun. And soon we will learn a new method for doing this kind of stuff called natural deduction. And the idea of natural deduction is to kind of simplify things, to take things that we know are true from truth tables and use them in certain ways. So we will come to that before too long. That'll be after our first exam for those that are in the class. Okay, so let's go ahead and go to part two. So remember, you're supposed to do part 2 and 3, so all of these. Part 2 says use truth tables to determine whether the following pairs of symbolized statements are logically equivalent, contradictory, consistent, or inconsistent. First, determine whether they are logically equivalent or contradictory. Then, if they don't apply, determine they're consistent or inconsistent. So the two pairs are like for number 1, tilde d wedge b and tilde parentheses d dot tilde b. These are our pairs. So logically equivalent means they have exactly the same truth table for every input. You get the same output. Contradictory means they have opposite truth values. If one is true, the other is false, and vice versa. If they are consistent, that means there's at least one line where they're both or all are true. And if they're inconsistent, that means there are no lines where they're all true. And the reason why they tell you to do one and then the other is because being logically equivalent or contradictory are the stronger relationships. So obviously, if they're logically equivalent, then they might be consistent or inconsistent depending on what the truth table says. But this already is a stronger relationship, so we don't need to look for that. So we look for these first, then we check for these. Okay, now this one is fairly easy because we're only given 2 propositions. Now you could be doing this with any number of propositions, 3, 5, 7, whatever. So just having 2 makes it somewhat simplified. But we do the same thing no matter how many propositions there are, which is to take our 2 propositions and compare them using a truth table. So on the one hand, we have tilde d wedge b, and on the other hand, we have tilde parentheses d dot tilde b. And you see there's only 2 propositions here, d and b. So we know that means there's going to be 4 conditions. So that's pretty straightforward. 2 propositions for scenarios. And that's the one where D comes out this way, and the one where B, in relation to it, comes out this way. So now we have our 4 scenarios here. And here the main operator is a wedge, so we'll apply this tilde to the D and get false, false, true, true, and then using these in the B column to get the wedge here, false and true, false and false, true and true, true and false with a wedge. Okay, and then always circling the main operator here. So now you can see true, false, true, true. Over here, using the same truth values for D and B, so true, true, false, false, and then tilde B is going to be false, true, false, true. So I'll just write false, true, false, true over here, and then repeat the D, sorry, true, true, false, false. And then the dot operator applied to these is going to give me false, true, false, false. Remember, if I'm going too fast for you, then I should be hearing from you at some point. Now the tilde applied to these is going to give me true, false, true, true. So now we have these, and we see, in fact, that every line is the same. So what that tells us is that when D is true and B is true, tilde D wedge B is true, and tilde parentheses D dot tilde B is true. When D is true but B is false, tilde D wedge B is false, and so is tilde parentheses D dot tilde B. Every line must be the same because they may have a couple in the same but then diverge. But then you see down here, when D is false and B is true, this sentence is true and this sentence is true. And when they're both false, this sentence is true, and so is this one. So for every one of these inputs, you get exactly the same output. So these are logically equivalent. They're logically equivalent because they have the same output for every input. The truth tables are identical. Okay, those are very good. Okay, so let's go ahead and do the next one here. Number 4. So number 4 is again one where we just have 2 propositions. It looks like R and S. And that simplifies things. So R wedge tilde S on the one hand. So we have R wedge tilde S. And then on the other hand, we have S dot tilde R. S dot tilde R. So we know we're going to have our four cases because there's only two propositions. So that's going to be like that. Then under R, we write true, true, false, false. And under S, I'll just do it over here. Rewrite true, false, true, false. That way I can write tilde S right here as false, true, and tilde R as false, false, true, true. And then using the wedge rule on these values, it's going to give me true, true, false, true. So circling the main operator. And then over here with the dot, we're going to have false, false, true, false. So now, are these logically equivalent? No. Are they contradictory? Well, let's see. When this one is true, this one is false. When this one is true, this one is false. When this one is false, this one is true. And when this one is true, this one is false. So indeed, these are contradictory. They're contradictory because they have opposite truth values. When one is true, the other one is false, and vice versa. So that is our clue. Oops, I gotta press select over here. That is our clue that they are in fact contradictory. Okay, so where's my eraser? Moving on to the next one. That was what, number 4? Okay, so next one is number 7. Don't want to accidentally skip these. Okay, so there should be a better way to erase everything that you have drawn. I thought maybe there was, but I don't know how to do it. Okay, so now we have on the one hand, so now we have 3 propositions, E, C, and L. So on the one hand, we have E horseshoe C in parentheses horseshoe L. And on the other hand, we have E horseshoe C horseshoe L. So this is a common mistake that people sometimes make when they're translating. They don't know where to put the parentheses. So this one's going to teach us that, in fact, these are, well, let's just look. So 1, 2, 3, 4, 5, 6, 7. So we know there's going to be 8 lines to the truth table because we have 3 propositions. And 2 to the 3 is 8. 2 times 2 times 2. Okay, so we have E, C, and L. So that means 4 truths, 4 falses under E. So 1, 2, 3, 4. 1, 2, 3, 4. And then 2 truths, 2 falses under C. True, true, false, false, true, true, false, false. And then under L, we alternate true, false, true. Oops, false. Dang it. What's happening? Okay. I must be pressing a button on my pen that I don't know about. True, false. Okay, so computing E horseshoe C, true and true makes true, then false, then false. And these are all going to be true down here. So now using this with this to get the main horseshoe operator, true and true is true, true and false is false. That's going to be true, that's true, that's true, that one's false, true, and then that one's false. So circling the, whoa, I'm getting a little squirrely there. Okay. So once again, we have our truth values over here. So I'll just kind of look under here. You could rewrite them under here if you wanted to, but I'll just use C and L. So true and true is going to make true. True and false is going to make false. False and true is going to make true. False and false is true. True and true is true. Whoopsie. That's true. True and false is going to make false. False and true is true, and false and false is true with the horseshoe. So now using E, And these values, so true and true makes true. E is true, and that's false, so that's false. True and true is true. True and true is true. You can tell all of these are going to be true because whenever the antecedent is true, it doesn't matter what the consequent does. We talked about that in our paradoxical material implications section on propositional logic in ordinary English. Okay, so now we just have to compare these. So both true, both false, both true, both true, both true, false, true, 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 false, true. So these are consistent with each other. These statements are consistent. They're not logically equivalent. They don't mean the same thing. There are cases where one is true and the other is false. So they have the same truth value in these lines here, but down here, there's this case where this is false and this is true. That's the case where E is false and C is true and L is false. And in the case where they're all false. Um, so in the case where they're all false, this one turns out to be false and this one turns out to be true. So they're close, but they're not the same thing. They are consistent with each other. Sometimes true. Excuse me. Consistent means there's at least one line where they're both true. So because of lines 1 and 3, 4, 5, and 7, that shows that there is at least one line where they're true together. Okay. So now then what we want to do is what's the next one? Number 10. Oh, allergies. Okay. So here we have but W, B, and T. So that's going to be another 8 line of our truth table here. So on the one hand, we have W and a triple bar and parentheses B dot T. And on the other hand, we have W and a dot to a parentheses of T horseshoe tilde B. Okay, so we know we need 8 because we have 3 propositions, so nothing has changed. So 1, 2, 3, 4, 5, 6, 7, 8. Should extend these over here. And then we know what we're going to do. By now, we're getting good at this. So we have 4 trues and 4 falses under W. 1, 2, 3, 4. Whoops, what did I almost fell for it, didn't I? You know what? I do have an eraser. So why am I always doing this? Um, Okay, so I was thinking about the next one as I was writing the last one. So 2, 2, 3, 4. Okay. And then B over here, we're going to have 2 trues and 2 falses. True, true, false, false, true, true, false, false. And then T is going to alternate true, false. So that's business as usual for our 3 propositions, false. Now go into the parentheses, apply the dot rule. So it's only going to be true when both of them are true and false in every other case. So that's going to be looking like this. And then the triple bar is only true when these match. So true and true will be true. And true and false is going to be false. True and false is going to be false. True and false is false. False and true is false. False and false, well, that matches. False and false, matchy. False and false, matchy. Okay. So now we have that one. So now we have to apply our T horseshoe tilde B. So B has true, true, false, false. So tilde B is going to have false, false, true, true, reversing those truth values. And then T is true, false, true, false, true, false. So I'll just look over here. True, false makes this false. False, false makes that true. True, true makes that true. False, true makes that true. True, false makes that false. False, false makes that true. True, true makes that true. False, true makes that true. Good. So now we have this one right here. And W, remember, had our four trues and four falses. So I'll just rewrite it just because things are getting, you know, two everywhere for me. Um, okay. So now we have this column and this column with a dot. So true and false, false, true and true, true, true and true, true, true and true, true, false and false, false, false and true, false, false and true, false, false and true, false. Um, this thing keeps, I don't know why I'm holding it in a funny way or something. I don't mean to be. Okay, so now we want to circle this. And now we'll inspect the truth table. So when this one's true, that one's false. False, true, false, true, false, true, false, false. Uh-huh. True, false, true, false, true, false. So this one is inconsistent. They're not exactly contradictory, uh, but close to it. But they do have this one case where they don't have opposite truth values, line number 5. So that makes them inconsistent with each other, which is simply to say that there are no cases where they're both true. So let's go ahead and do the next one then. I think there's one more in this section. So that's number 13 over there. Oh, excuse me. I don't know when these allergies are going to let up, but I assume at some point or not. All right, so this last one here, once again, it looks like we have three propositions, H, J, and K, H, K, and J. Okay, so um, we know we're going to have our 8 lines once again. So we do H dot K wedge J, and we want to compare that to this one over here, which is J dot H wedge H dot K. So J dot H wedge H dot K, H dot K. So I already know that these are going to be logically equivalent. This is a very famous rule, which we might learn later in the semester. Depends on how far we get into natural deduction, but this is called distribution. So, but nonetheless, let's prove it. So, get our 8 cases here. And we do the same thing we always have done. So 4 trues and 4 falses under H, 2, 3, 4, and then 4 falses, 2, 3, 4. And then K alternates true, true, false, false, true, true, false, false. And then J alternates true, false, true, false, true, and false, and true, and false. Good. So now applying the wedge operator in here, this is going to be true, 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 false, true, 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 false. Pretty standard. Now applying the dot operator across here, true and true, makes that true, true and true, true and true, true and false, false and true, You can see that's going to be false all the way down because of the F on this side, and the dot requires them both to be true. Yo, okay, here we go. Whoa. Okay, getting a little creative with my lines here. Okay, so now over here we have J and we have H. So J is the alternating one. So that's true. I'm just going to rewrite it because there's too much going on here. Alternating. And then H is the four trues and four falses. 1, 2, 3, 4. 1, 2, 3, 4. And then you put a dot between them and you get the following. Okay, so false, false, true, and false. Yes, yes, yes. True, true. All right. So now H is here, and then K is the one that has two. So let me just rewrite K. Wait, true, true, false, false, true, true, false, false. Okay. Now H is right here and K is right here. So true and true makes that true. True and true makes that true. True and false makes that false with a dot. So that's false. False and false. False and true. False and true. False and false. False and false. Okay. Now we want this and this with a wedge to get the main operator. So true and true with the wedge is fine. False and true is good. True and false is true. False and false is false. 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 And false and false is false. Said false a lot right there. Seems like false and false and false. Okie dokie. Now we'll compare them. True, 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 false, 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 false. So you can see, as predicted, these are logically equivalent. For every input that you get the same output. Later, we find out that these are nice because whenever you have logically equivalent statements, you can replace one with the other. And that's a time saver in many cases for lots of things we want to do later. Okay, so, but we'll do that later. Don't worry about it right now. Right now, we're just kind of proving that they are logically equivalent according to the definitions that we have been given. Remember, these definitions are not magic. These were constructed largely to mirror what we take as kind of intuitively to be the case in many ordinary English arguments. But as we'll see later, there is some dispute about whether these are the right definitions for the operators. But for now, we're just trying to learn them. All right, so we did all of those. I think that's everything. Okay, good. So now over here, these ones say use truth tables to obtain the answers to the following exercises. The letters to be used in constructing the truth tables are given in parentheses down here. So we're going to be doing the same thing, but now we're trying to figure out how to answer these questions. So this one says, renowned economist Harold Carlson made the following prediction. The balance of payments will decrease if and only if interest rates remain steady. However, it is not the case that either interest rates will not remain steady or the balance of payments will decrease. And then the question is, what can we say about Carlson's prediction? So what we're going to have to do is translate this argument into symbols, then construct a truth table for it, and then see what the truth table tells us. Okay. So in quotes, we have the balance of payments, that's B. So B stands for the balance of payments will decrease. And I stands for interest rates remain steady. So this if and only if right here, that's the triple bar. So this says B triple bar I. B triple bar I. That's the balance of payments will decrease if and only if interest rates remain steady. Then there's this semicolon, however, and we know from our explorations of this that means and. If you don't know that, then you need to go and refresh your memory by looking at the video translating English into propositional logic. Um, so it is not the case that either. So when you have it is not the case that either, that's a tilde, and this is going to introduce a wedge. So the wedge is going to be here, and what's on either side of the wedge is what comes in between the either and the or. So we're going to know that this is a tilde, and there's going to be a parentheses, and we're going to have interest rates will not remain steady. So that's tilde I. And then there's a wedge, and the balance of payments will decrease. That's B. Okay, so this is what Harold Carlson said. He has two propositions here, so we know there's only going to be 4 lines of our truth table. So 2 to the 2, and 4 conditions are where they're both true, where one or the other is true, or where they're both false. All right, so that's it. Now the triple bar requires matchy-matchy, so that's going to be our kind of standard triple bar case. They only match in the first and the last one. So we're going to look at this and whatever's over here, ultimately to get the truth value for the dot. So now tilde I is going to reverse the I statements. So that's going to be false, true, false, true. And when you wedge that to B, so true and false gives you true, and true gives you true, and false gives you false, and false and true gives you true. So that's B over here and tilde I here. And this tilde applies to in here. So that's going to give you false, false, true, false, just reversing these values. And now we look here and here for the dot. So true and false with the dot is false. False and false with the dot is false. False and true with the dot is false, and true and false. Okay. So what this guy said was self-contradictory. So he's trying to make a prediction here. His prediction, what can we say about his prediction? Well, it can't possibly come true. It's going to always be false. He said something self-contradictory. Okay, so let's go ahead and do some more. Now, these kinds of things are, I will have it, you can, if you're in the class, you can count on there being some problems similar in some way to these kinds of problems, word problems, in other words, where you have to take translation and then use truth tables to figure out what the answer is. Okie dokie. So going on to number 4, says 2 astronomers are discussing supernovas. Dr. Frank says research has established that if a supernova occurs within 10 light years of Earth, then life on Earth will be destroyed. Dr. Harris says research has also established that either a supernova will not occur within 10 light years of Earth, or life on Earth will not be destroyed. Is it possible that both astronomers are correct? So possible they're both correct. They're asking us about whether it's consistent, whether what they say are consistent with each other. So truth table will answer that. And if so, what can we determine about the occurrence of a supernova? So that's going to require us to compute the truth table and then look at the cases where they're consistent, if it is. Okay, so research has established that what? Well, if a supernova occurs within 10 light years of Earth, that's S. S, where to go? Then life on Earth will be destroyed. That's L. So S horseshoe L. Research has established that, says Dr. Frank. So research has also established that either a supernova will not occur within 10 light years of Earth, or life on Earth will not be destroyed. So that's either no supernova or not Earth lacking life. Okay, so those are the 2 statements. And now we just want to know, are they consistent? We have 2 propositions. So we know that we're going to have 4 lines to our truth table here. And we know that this is going to be pretty standard. Both true, one but not the other but not the one, and then both false. So this is going to be the standard definition of the excuse me. So now these are going to be reversed. So this is going to be false, false, true, true. This is going to be false, true, false, true. The wedge is going to be false, true, true, true. So now we've computed both of these. So true, false, false, true, 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 true. So yes, lines 3 and 4 here show that they are consistent. They are consistent with each other. And what's it says? It says, if so, what can we determine about the occurrence of a supernova? Well, S what supernova will occur. And the case where they're both true is the one where S is false. So where S is false, what does S say? Supernova will occur within, excuse me, supernova occurs within 10 light years of Earth. So they're both true in the case where there is no supernova, where it doesn't occur. That's what this being false means. So they are consistent, but only in the condition that there is no supernova within 10 light years of Earth. Okay, so fun stuff. Now moving on to number 7 here, which is down a bit further. So let me, oops, I got to erase that over there as well. So number 7 says, two stockbrokers are having a discussion. One claims that Netmark will introduce a new product if and only if both DataPro cuts its workforce and CompuCell expands production. Okay. The other claims that DataPro will cut its workforce and CompuCell will expand production if and only if Netmark introduces a new product. Is it possible that they're both right? If so, what have they told us about these companies? So this is another one where they're asking us about whether these things can be consistent with each other. Now we have 3 propositions. So that means 8 lines of the truth table. So we're going to have to translate these into symbolic form, then construct a truth table and determine whether or not they can both be true, and if so, under what conditions will they both be true? So let's translate these. So this is the first guy or person. Netmark will introduce a new product if and only if. So Netmark introduces a new product, that's N. So Netmark will introduce a new product if and only if, and then what's it say on the other side? If and only if both, that means and. DataPro cuts its workforce, that's D, and CompuCell expands productions, D dot C. So that's the first statement. And we know that we're going to have 8 lines of our truth table here. So let me draw those out real fast. 1, 2, 3, 4, 5, 6, 7, 8. And we need liney lines across. It was easier to work on the other side. Now, I did try to have the book and a whiteboard open at the same time when I was recording these videos, but there's no way Zoom says you can't do it. So I have to do it this way. Okay, so the other person here says, DataPro will cut its workforce, there's a comma, and CompuCell will expand production if and only if. So that's a cuts its workforce and expands production. If and only if, triple bar, Netmark introduces new product. Okay, so can they both be right? Well, let's find out. So under N, we're going to do what we always do, which is write 4 trues and 4 falses. And now under D, we write 2 trues, 2 falses. True, true, false, false. And under C, we're going to alternate true, false, true, false, true, false, true, false. And then apply the dot to here, gives us true, false, false, false. Then true, false, false, false. So now we have this thing here and this thing here applied to a triple bar. So true and true, matchy, matchy. True and false, no matchy. True and false, no matchy. True and false, no matchy. False and true, no matchy. False and false, matchy, matchy. False and false, yes, matchy. False and false, matchy. Okay, so truth values are the same. The triple bar Says cool. All right, good. So now we have that. So over here, um, we have D dot C. So we already know the truth values for D dot C that we wrote them already right here. So true, false, false, false. So I'll just rewrite them. True, false, 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 true, false, false, false. And then N was our four truths, four falses, four truths. I'll just rewrite that so I don't go making mistakes, hopefully. That's a false. And then matchy matchy makes true. No matchy, no matchy, no matchy, nope. Yes, matchy. Yes, matchy. And that's yes. Okay, so what can we say about what these guys said? Let's look. Well, this is true and that one's true. False, 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 false. True, 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 true. They said exactly the same thing. These guys both said something that means exactly the same thing. So what they said was logically equivalent. There's no difference between their statements, logically speaking. Okay. So that's fun. It's always nice to say logically equivalent things. All right. So now I think there's one more on the other page. So let's just make sure we get that one before we are finished with this. All righty then. Lots of erasing to do. Almost as bad as actually in class, except then I have a marker all over my fingers. Okay, so then finally number 10 here. Oh, I need to erase that. I'm not going to have enough room here. Is there room on the other page? Maybe no. And I need 8 lines. Okay, so definitely going to have to sort of try to write it up here. All right, so let's see. It says Nicole Ramirez, yes, expresses her philosophy as follows. If the mind is identical to the brain, then personal freedom does not exist and humans are not responsible for their actions. If personal freedom does not exist, then the mind is identical to the brain. Either humans are responsible for their actions or the mind is not identical to the brain. If personal freedom exists, then humans are responsible for their actions. Is it possible that Nicole's philosophy makes sense? If so, what does it say about the mind, personal freedom, and responsibility? So for it to make sense is to ask if it's consistent. So what they're asking us is, can all of the things that she believes be true at the same time? Okay, so we're going to need 8 lines of the truth table. And she said a lot of stuff. So let's see. If the mind is identical to the brain, then personal freedom does not exist. So that's if the mind is identical to the brain, then personal freedom does not exist. Okay, so that's one. Oh, and humans are not, I missed it. Oh, sorry about that. So that's going to be a parentheses on the other side. So we can tell there's a parentheses because there's this comma right here. And then she says, then personal freedom does not exist and humans are not responsible for their actions. So that's dot tilde H. Okay. If personal freedom does not exist, then the mind is identical to the brain. So that's one. So if personal freedom does not exist, then the mind is identical to the brain. That's a P. Tilde P horseshoe M. Either humans are responsible for their actions or the mind is not responsible. What? Or the mind is not identical to the brain. So either H or tilde M. Okay. I'm not going to have enough room over here. If personal freedom exists, then humans are responsible for their actions. That's P horseshoe H. P horseshoe H. Okay. So I don't really know if I'm going to be able to pull this off over here, but we know there's going to be 8 cases. We know that because, can I scroll up a bit? Yeah, okay. So that bottom of the page was annoying me. All right, so if we did everything right, we should have everything we need up here. A little bit annoying that that star 7 is going to be in our way, but we still should be able to be fine here. Okay, so now we have M tilde P tilde H. So under M, we're going to write 4 truths, 4 falses. Okay, so that much we know for sure. So 1, 2, 3, 4. 1, 2, 3, 4. Okay. Now P is going to get 2 truths and 2 falses. I'll write it over here just because this one is tilde and that one is tilde. So I'll write it under this one, which doesn't have a tilde in front of it. 2 truths and 2 falses. True, true, false, false. True, true, false, false. And then H is going to alternate. I'll write it here just because there's more room than over there. So it doesn't really matter as long as you are consistent about this, you'll get the same answer. Okay, so now tilde P and tilde H are going to be reversing of these ones. So tilde P is going to be false, false, true, true in the way we're doing things here. Pen. Okay, so I'll write false, false, true, true. For the tilde, false, false, true, true, false, false, true, true. And then H gets false, true, false, true, alternating. So now I can compute the and here. So that's going to be false, 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 true, false, 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 true. So now using this and this with the horseshoe, true and false makes false. True and false makes false. True and false makes false. True and true makes true. False and false makes true. False and false is true. False and false is true. False and true is true with the horseshoe. So now this is the truth values for that sentence there. Okay. So now tilde P and M. So here's tilde P, here's M. So false and true makes true. False and true makes true. True and true makes true. Tilde P, true and true makes true. And these ones here with tilde P, false and false, that's going to be true. False and false, true. True and false, nope. And true and false, nope. So there we go. And then H wedge tilde M. I guess I didn't reverse the tilde M's anywhere. So 4 falses, 4 trues. All right. And then the wedge, true and false makes true. False and false makes false. True and false makes true. This one is false. True, 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 true. Okay, so that doesn't leave me a lot of space here. But nonetheless, okay, there we go. And then P, horseshoe, H. H is over here, P is here. So true and true makes true. True and false makes false. False and true makes true. False and false makes true. True and true makes true. True and false makes false. False and true, false and false. Okay, so now circling this. All right, so I think I did it right. Hopefully we did it right. Now we want to see what we can say about these sentences. So false, true, true, false, 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 true, 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 false, true, 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 true. So line 5, they're all true together. True, true, false, true, true. So is line 7. And true, true, true. So is line 8. So these are consistent. Her philosophy does make sense. What did it ask us again? It says, is it possible that Nicole's philosophy makes sense? Yes, They're consistent. There's three cases under which these are consistent. If so, what does it say about the mind, personal freedom, and responsibility? So, um, what does it say? Well, let's look at the case. What happens when they come out to be true together? So, M is false. P is true and H is true. So M is false. What was M? M was the mind is identical to the brain. Um, okay. So in every case where they come out to be true, M is false. So in order for her philosophy to make sense, the mind is not identical to the brain. Okay. Um, and number 5, 7, and 8. Um, and humans do have responsibility. Sorry. Um, so true, the mind is not identical to the brain. Sometimes people do have personal responsibility. And what was P again? Oh my gosh, this is why having it all on the same. Personal freedom exists. Okay, so the mind is not identical to the brain. That much we know has to be true. But what about personal freedom? Well, in one case, personal freedom does exist and humans have responsibility. That's line 5. Line 7 is that we don't have personal freedom, but we do have responsibility. And in the other case, we don't. So really, we may or may not have personal freedom, but we have to be responsible, and the mind is not identical to the brain. That seems to be largely what this is telling us. What did I do wrong here? So 5, true. Oh, seems to be largely what this is telling us, but I feel like I'm doing something wrong. Oh, I am doing something wrong. So in these lines right here, I wasn't overlooking. I should have circled this just so I don't go cross-eyed. But in this case, we have it being false right here. So these ones, it's only line 5 where it comes out to be um, true. And in that case, the mind is not identical to the brain. We do have personal freedom, and humans are responsible. We do have uh, personal freedom, and humans are responsible. So if her philosophy um, makes sense, there's a line where it's all consistent. And in that case, what has to be true is that the mind doesn't equal the brain. We do have personal freedom, and humans are responsible. So that one was a bit tricky. But if so, what does it say about the mind? Okay, so that's what it says. The M is false and P and H are true. Okay. All right. So I think that's all of them for this section. Join us next time for more exciting adventures in propositional logic. How do I stop this crazy thing?